Bismillah ar-Rahman ar-Rahim. When the real part of alpha is strictly greater than 1, the function zeta of alpha is given by the sum over positive integer g of 1 over g to the power alpha. The domain of the zeta function can be extended to include the whole complex plane except when alpha is equal to 1. In this video, the focus is extending the domain so that it includes the part of the complex plane where the real part of alpha is strictly greater than -2, excluding alpha equal to 1. Our tool is the Euler Maclaurin formula, which quantifies the difference between a sum and a closely related integral. I'll focus here on a special case. Consider function g. The mth derivative of function g is denoted by g superscript m between brackets. We assume the existence of the third derivative. We have two non-negative integers, a and b. A is less than b. Let's focus on the integral of g from j to j plus 1. J is in the set from a to b minus 1. We will spend some time investigating this integral. Then we will simply sum over j from a to b minus 1. This gives us the integral of the function g of x from a to b. Do the change of variables, y equal to x minus j. So x is y plus j. When x is j, y is 0. When x is j plus 1, y is 1. dx is dy. Let's do integration by parts. I write this dy as d of y minus 1/2. We can of course write dy plus any constant. I will shortly comment on this choice of -1/2. We need to take the limit of this product of y minus 1/2 and g of y plus j, as y tends to 0 from above and tends to 1 from below. When y is 1, we get 1/2 g of j plus 1. When y is 0, we get -1/2 g of j plus 0. That's g of j. We subtract. So we get the arithmetic mean of g of j and g of j plus 1. We then have minus integral y from 0 to 1, y minus half times the first derivative of function g. If function g is a linear polynomial, its first derivative is a constant that can be taken outside the integral. We then have integral y from 0 to 1 of y minus half. The antiderivative is 1/2 y minus 1/2 squared. We get the exact same value when we use 0 or 1. This integral is equal to 0. The choice of this 1/2 here is so that if function g is a linear polynomial, then this term vanishes. We have this picture. Indeed, the integral is equal to this part here. Let's do integration by parts again. We have y minus half dy. I write it as d of 1/2 y squared minus 1/2 times y plus a constant. When we do integration by parts, we get this quadratic polynomial multiplied by the second derivative of g. We want the integral to be 0 if this second derivative is constant. On that basis, we compute the value of c. This way of doing things will generate for us the Bernoulli polynomials. For this part, when y is 0 or y is 1, we get 0 from here. This part is minus c, the first derivative of g at j plus 1, minus the first derivative of g at j. We choose c so that this integral is equal to 0. The integral is equal to c minus 1 over 12. So c is 1 over 12. This is the formula that we have now. We will do one more step of integration by parts. This is enough for our purposes. The antiderivative of this part is 1/6 y cubed minus 1/4 y squared plus y over 12 plus a constant. This integral is equal to c bar if we want it to be equal to 0, so that this integral is 0 when this is constant. We must choose c bar to be equal to 0. And when c bar is equal to 0, this part here is equal to 0, whether y is equal to 1 or is equal to 0. There is no term involving the second derivative. This is the formula we will use in our investigation of the zeta function. Let's rewrite this integral using variable x. Y is equal to x minus j. So we will get an integral from j to j plus 1. We have the third derivative of g. Note that x is a real number between j and j plus 1. So j is the floor of x. X minus j is x minus its floor. This is the fractional part of x. So here is the integral with the third derivative, and this part, which is the third degree Bernoulli polynomial. We sum both sides, j from a to b minus 1. So this integral is from a to b. That integral is also from a to b. We have this sum here. Note that we are summing g of j plus 1. So this sum starts from g of a plus 1 plus g of a plus 2 all the way to g of b. I write this sum starting from g of a. It is not here, so I need to subtract half g of a. This sum is g of a plus g of a plus 1 all the way to g of b minus 1. Again, I write it as a sum from g of a to g of b. Then I subtract half g of b. Summing this part is a bit easier because it is telescopic. We have the first derivative evaluated at j plus 1 minus the first derivative evaluated at j. So when we sum, we will get this term with j equal to b minus 1. So this is the first derivative evaluated at b. We have minus this term with j equal to a. That's the first derivative evaluated at a. These two terms together are the sum j from a to b of g of j. Let's have this sum on one side, move everything to the other side. What we have on the other side is the integral of g of x from a to b. When these guys join the side of the integral, we get the arithmetic mean of g of a and g of b. Then we have this part here with the plus sign. The bracket is multiplied by 1 over 12. Then 1/6 integral x from a to b, the third derivative of g, multiplied by this Bernoulli polynomial, whose argument is the fractional part of x minus its floor. Let's think about this polynomial. Consider h of y cubed minus 3y squared over 2 plus y over 2, and y is between 0 and 1. Recall that the floor function is greater than or equal to 0 and is strictly less than 1. If we try to upper bound the magnitude of this part, by the triangle inequality, the magnitude is upper bounded by 1 over 6, integral from a to b, the magnitude of the polynomial times the magnitude of the third derivative of function g. So what is the maximum magnitude of this polynomial? We can use standard calculus techniques to find that this cubic polynomial has a local maximum and a local minimum on the open interval from 0 to 1. In magnitude, both are equal to 1 over 12 times the square root of 3. So this part here in magnitude can be upper bounded by 1 over 6 times this number, and then the integral of the magnitude of the third derivative of function g. We now make the specific choice that g of x is 1 over x to the power alpha. The real part of alpha is greater than 1. The integral of x of minus alpha is x to the minus alpha plus 1 over minus alpha plus 1. Then we use the limits of integration. We get this term here. These are the first three derivatives of function g. That part is the term here with the first derivative. This is the integral with the third derivative. Set a equal to 1. We get these three terms, 1 over alpha minus 1 plus 1/2 plus alpha over 12. These are the terms that depend on the upper summation limit b. The integral now is from 1 to b. Based on our upper bound argument, the magnitude of this part is upper bounded by alpha plus 1, alpha plus 2 over 72 square root 3. The integral x from 1 to b of 1 over x to the alpha plus 3. This integral is 1 over alpha plus 2 between brackets 1 minus 1 over b to the power alpha plus 2. If the real part of alpha is greater than minus 2, then this function of b decays to 0 as b tends to infinity. We get a finite result. Let's rewrite this line by taking those functions of b and moving them to the sum j from 1 to b of j to the minus alpha. On the right hand side, we have those three guys and the scaled integral. If the real part of alpha is greater than 1, and we take the limit as b tends to infinity, this goes to 0, this goes to 0, and that goes to 0. This summation becomes zeta of alpha. What if alpha is 0 or alpha is equal to minus 1 or any value that violates this inequality? When we take the limit of this side as b tends to infinity, we get those three terms and then this scaled integral x from 1 to infinity. And we know that we get a finite result so long as the real part of alpha is greater than minus 2. So we take this function of b and we define zeta of alpha to be the limit of this function as b tends to infinity. If the real part of alpha is greater than 1, this is the original definition of the zeta function. The sum is zeta of alpha. Those three terms tend to 0 as b tends to infinity. If this condition is violated, but alpha is not equal to 1, and the real part of alpha is greater than minus 2, we get a finite result for this limit, and this is zeta of alpha. Alpha now has a real part greater than minus 2. We always exclude the case that alpha is equal to 1. If we choose to extend the domain of the zeta function using another method, we will end up with an extension that also gives the exact same values. This is a powerful result in complex analysis, the uniqueness of analytic continuation. I won't get into details, but the point is that there are several ways for extending the domain of the zeta function, but all of them, done properly, will give us the exact same values. So the zeta function is well defined and is finite on the whole complex plane except when alpha is equal to 1. We are able now to know what is zeta of 0 and zeta of minus 1. The good news is that this scary integral is multiplied by alpha. So when alpha is 0, this part is 0. It's also multiplied by alpha plus 1, which is 0 when alpha is equal to minus 1. We don't really need to think about this integral. Zeta of 0 is 1 over 0 minus 1, that's minus 1, plus 1/2 plus 0, that's minus 1/2. If alpha is equal to minus 1, this term is minus 1/2, plus 1/2, that's 0. Zeta of minus 1 is minus 1 over 12.